All right, so we're starting our third sprint this week. These things are called sprints because it's from an agile software development methodology where you split up work for a larger project or an ongoing project into smaller and smaller periods. Usually it's about 4 weeks, but of course, since this is just one semester, our sprints are about 2 weeks. We've already organized them into sprints for you, but in a real situation, in a real software development methodology thing, your team would be self-organized, and you would identify these sprints. At the beginning of the sprint, you commit to a certain amount of work. At the end of the sprint, you look back and say, okay, did we meet our goals? If not, how do we adjust for next time? What went well? What didn't go so well? And I try to model that with all of our retrospectives. Right now, we're grading all of the assignments, and we should have those out on Thursday with yet another retrospective of what went well, what didn't go so well, et cetera. What you should be doing right now is you should be reading that and understanding the handout, going back to the project overview to understand more about the business rules so that you can start drafting your design document starting tomorrow. Along with that, you should also be planning the rest of your sprint. If you're working with somebody, again, you should be working out, we're going to work on this day, this day, this day, and we're going to be doing this, this, and this. By the way, I've got something coming up 2 weeks from now. We're going to have to plan around that, and so I'm going to have to change the schedule here so that we don't have one pad day at the end. Instead, we move that up, and we start working on the weekends or something like that that are not scheduled for anything. So there's where we are in the Gantt chart. We're all fresh. Now, if you did have problems on your first assignment, or in the first phase, I should say, it didn't work 100%, or there were design flaws that we'll be identifying and then telling you about when we release those grades, those need to be fixed first, right? Because like if you didn't turn in a working version at all, which a lot of people did, you're stuck. You're stuck spinning your wheels until you get that working, and so you can move on to the next phase. All right, so there's our Gantt chart, and there's where we are. To pick up where we left off last time, we were talking about polymorphism. And in general, remember that polymorphism is a code, a variable, a method, or a class that can be generically applied to more than one type. Polymorph, more than one form. So that you only have to write one sorting algorithm. You only have to write one get max algorithm or something like that. And then you can apply that to any other type. Programming languages like C, they have this kind of generic programming, but it's not as strong as it is in Java. Even something like Python has this generic programming, but as we saw, that it also falls short. And now as we're going to see that it also somewhat falls short in Java here because of where we left off. Remember, we were looking at creating 2 savings accounts and 2 annuity accounts, and I simply just wanted to add up the total of all my accounts. We started out with a solution here that took a set, and then we said, well, wait, what if I had a list, right? Or vice versa or something like that. If you had a list of bank accounts, a set of bank accounts, and so we changed that so that it took a collection of savings accounts or a collection of annuity accounts in this case. And then we got stuck on this part. Why are we getting stuck on this part? Let's go ahead and read the complaint here, or what the compiler is complaining about. Now, remember that we also covered operator overloading and method overloading. Remember, unlike C, you don't have to have abs, fabs, labs, and labs. You just have one absolute value function, and there are name, and there are actually 4 functions. One that takes a double, one that takes a float, one that takes a long, one that takes an integer. At compile time, depending on what you gave to that method, the compiler is smart enough to figure out through static dispatch which one of those that you meant to call. Unfortunately, the compiler is not smart enough to do that over here. Right? So you might look at this and say, well, wait a second. This is a collection of savings accounts. This is a collection of annuity accounts. Of course you're smart enough to figure this out. Down here where I give you a collection of savings accounts, you should be able to call that first one. Where I give you a list or a collection of annuity accounts, you should be smart enough to figure that out that other one. It's not, but it's not because it's dumb. It's because of history. So let's go ahead and read the complaint here. Erasure of method sum values is the same as another method. So now what we need to do is we need to understand what is called type erasure. This awesome parameterization was only introduced in Java, I want to say 6, maybe, yeah, I believe Java 6, 5 years after the first Java was officially released. So even though for the last 21 years or so, we've been living in a world where we've got these parameterizations, it didn't always exist that way. And one of the defining design principles of the Java programming language is we want to make sure that we're absolutely backwards compatible, to the point where they will bend over backwards to make sure that it's backwards compatible. So in 2000, 2001, whenever it was, they decided, well, we need some parameterized polymorphism here because it's great. How do we do that without breaking the last 5 years of code? They had a decision to make. They could go ahead and break the last 5 years of code and just have strong parameterized polymorphism, or they could bend over backwards and make sure that it was backwards compatible. They chose the second option. Whereas, say, a programming language like Python, right? Let's look at Python over here, right? Where is it? I don't remember where I mentioned it. But those of you that learned Python, did you learn Python 2? Or did you learn Python 3? Why? Because at some point they said, look, there's lots of warts, there's lots of bad things in this language. We can either continue as we've been doing and make this backwards compatible, or we can say, nope, we're going to have a cutoff point here. At some point, we're no longer going to support, we'll go ahead and keep 2 and 3, but 3, we're not going to be saddled with all those warts and flaws and design issues that we had in 2. Right? Instead, we're going to make not a completely brand new language, but a non-backwards compatible language, Python 3. And at this point, Python 2, I think, has reached its end of support life, right? LTS or some long-term support. Java is different. They decided, no, we do not want that. We want to make sure that it's backwards compatible. So what happened was, when they introduced parameterization, they had a compromise. They said, all right, we'll have the compiler go ahead and take these parameterizations into effect, but when it actually gets compiled to Java bytecode, it gets erased. That's what type erasure is called. Here, let me prove it to you. Let me go ahead and get rid of the second one, and let me get rid of some code down here so that it actually compiles. Right. Oops, I just want this out. There we go. Right. So there, now it compiles and it will run. Right. Let's take a look at what it actually looks out on the system. When Java files are compiled, they're compiled to .class files, which you can open up because some of it is actually plain English. Some of it is bytecode that you're not going to be able to look at because it's just bytes, right? It's just binary. But other parts of it are parts that you can actually look at. There's our sum values collection. Do you see that parameterization there anymore? No, it was erased. Type erasure. This was their compromise 21 years ago. It's a compromise that we're still living with today, which means that we can't do stuff like this. There is a workaround solution. Well, the obvious workaround solution would be what? New name, exactly. Go the C route. Some values for savings. Some values for annuity, right? I don't want to follow that. Right? So let's go ahead and get rid of both of those. And let's think about another solution. A savings account and an annuity account are, guess what? Both accounts. Right? So if I treat them just as a regular old account, I can do something like this. Right? There we go. Now that compiles because there are not two methods anymore. But what about down here? Some values and some values. We have a different issue now. In the demo is not applicable for the type set of savings. Even though they're subtypes, even though savings and annuity are both accounts, remember, type erasure. When that goes away, is that information there anymore? No. So the actual solution that they came up with when they introduced this is named parameters, okay? And let me go ahead and try it like this. Static, there we go. So what that is a Langle-Wrangle. What I'm doing there is I'm saying that there is a type in this function called t. Is t a string? Is t an integer? Is t an account? Right? It can be anything you want it to be. When you call this function, you will pass it a collection of type t. Not accounts, not savings accounts, not annuity accounts. Instead, t. What happens is that blank t gets filled in. You can think of this as type. right? And you can actually use type if you want to. It's just a variable, but it's not a variable with a value. It is a variable for the type itself. Don't do that, though. That's not usual, right? Okay, great. Now down here, all my problems are solved, right? If you want to call this sum values, then call it on a set of savings. That works. Call it on a list of annuities. That works. But what's the problem? That just shifts the problem to up here. Right? Am I going to be able to treat these as accounts anymore? What are these things? This is a list of what? T's. Right? What is a list of T's? Does everything have a get value function? Nope. So what I'm going to have to do is I'm going to have to put a minimum amount of information in here that these things are in fact accounts. Extends account. Right? The magic, right? All of my problems are now gone. I have one function to rule them all. I can go ahead and give you a list of annuity accounts, a set of savings accounts. I could put them all into one list, and I could sum them all up at once. Right? And that's because I've got this named parameter, and I have a minimum amount of information about T. They have to be accounts. It can be a savings account, an annuity account, or accounts themselves. I couldn't do something like this. Say a list of strings. Or string, spell it right? Right? Foo is equal to new array list of string. Sorry, I never even bothered to check to see if it's working. No complaints online, so good. How many are watching? Oh, thank you for the other person watching. Good. One other person besides myself, right? All right, so I'll go ahead and try, summing these values, right? Foo. There we go. Is it going to work? No, because our strings accounts? No. By putting in this minimum amount of information, I'm able to have a get value function out of that. You can take this further. Did I ever actually use the T in this function here? No, I could have. I could have said, all right, well, I'll go ahead and say T first account is equal to accounts dot get the first one, right? Something like this if it were a list instead, right? And what type is, and I'm not going to do this, so the way to do this with a general collection is an iterator, and then dot next. There we go. We'll see this in a second here. I'm not actually using that variable, though, am I? All right? Uh-oh. We're good on live streaming. Okay, yeah, we are. No power out, or no Wi-Fi outage yet, right? But if I had created a variable of type T, then I would have needed to use this T. Then I'm using that T. I'm not actually doing that, though. Who cares, right? So let's get rid of that. If you're not actually going to use the fact that the name T, you don't have to put it in there. Question mark and question mark, right? That's not the way to do it on the left-hand side there. But what is this question mark here? It's not compiling, but it will compile here in a second after I take care of it. What is that question mark? What does a question mark mean? What type is it? I don't know. I don't care because I'm not actually using it. I never actually made reference to T's. And so I'm going to go ahead and get rid of it. Now the way to do this is by putting it over here exclusively. There we go. And now it's even more general and generic, right? It doesn't have to be any particular type as long as that type is an extension of an account, right? And you're not going to use it down here, then who cares? Right? And there is my ultimate solution. If I go any further, then, I can't go any further. I would lose information about these being accounts, right? All right. So that is parameterized polymorphism. Some notes on this. Again, you can't use the subtypes in parameters due to type erasure. And it gets into something that's called PECS, P-E-C-S, right? Which stands for Producer Extends Consumer Super. Now to understand that, I've got, I thought I had it. Let me go ahead and pull up my, sorry. I thought I had it up and running, but no. This is the one time that I'll use some old school slides. Here we go. Find get max. There we go. All right, so I'll bring this over here. Here's another example where I want to write one get max function. Okay, That is, if I've got a list of numbers, right, then I want the maximum value in that list of numbers. If I've got a list of strings, or a collection of strings in this case, I want the maximum string. In other words, the one that starts with Z, right? Something like that. If I've got a list of bank accounts, I want to get the maximum bank account with respect to the value, the account with the most money in it, right? So you might start out with a parameterization that looks something like this. I parameterize it to T so that it can apply to numbers, strings, and bank accounts. I give it a collection of elements of type T. I get the first one, and then I go through for each other one. I compare them. Is this larger than the maximum I've found so far? If so, update the maximum to be the T, and then return the max at the end. The problem is that this is not real Java code. Do you have any information here about T's in order to compare them and say that, well, 5 is bigger than 3, so therefore this is the maximum? Is there anything there that tells you that, that would give you that clue? No. So what you need is a minimum amount of information. Let me jump forward here. There we go. If I say that T extends number, then that means that it can apply to integers, floats, longs, doubles, whatever type of number that you want. All of those built-in types are numbers. They inherit from number. And now that gives me a minimum amount of information to work with here. What I can do is I can take the maximum value and T, and I can dump them to the most general double value. And then I can go ahead and compare them. Does that solve my problem? And I did that by saying that it extends java.lang.number. Does that solve my problem for strings? No. So I need another more general solution. Right? And there we go. I'm going to say that T extends comparable. Remember comparable? We made person comparable a couple weeks ago. And we said that this person and this person, if this person's last name comes before this person's last name, then this person comes first. If they have the same last name, then we compare them by their first name, right? And that means that we're going to have T, which implements the comparable interface for other elements of type T. Because then that gives us the minimum amount of information that we need. We've got this compare to method. T compared to that thing over there, right? Do I have any more generalization? No, not yet. We'll come back to this here in a second, right? What's another way that I could have done this? I'll just preview it here. Public static T get max, right? I'll take a collection of elements of type T, right? And I don't want to have any other information. I don't even want to impose the condition that it has to be comparable. Instead, what else should I take over here? And this is not the question mark of the non-named parameters. What's the other thing that would help you to say that go over this collection and this one and this one? Oh, this one comes first, or this one is larger than that other thing. A comparator function, not a comparator function, but a comparator class for elements of type T. Right? Now I have all the information that I need here. I'll just call this foo, right? And I'm not returning anything yet, right? Here's my collection of elements of type T, my comparator for elements of type T, and I just simply pass off responsibility to that comparator. In fact, this is so useful. Guess what? Just like sorting, just like searching, it's already written for you in the collections dot max function. Right? Let's take a look at what it looks like. It's even more complex. Right? So T extends either object, and it has to be comparable, or you have, or not this one. Sorry, I want the other one. Where's my max? There we go. The maximum with a comparator. Right? In fact, this was the last solution right before this solution that I proposed. This one over here. It's basically this solution right here. This is the one that I want to look at, though. Right? It's parameterized, T. Right? And I can't make a T with one hand. Right? It's going to return an element of type T, the maximum element. It will take a collection called col in this case, and it's got that erasure there, right? Question mark. Who cares? Right? But it extends elements of type T. And here's a comparator for elements of type T. And this is a little bit new. This is something I haven't talked about yet. Question mark super. That's an upper bound. We're upper bounding and we're lower bounding these things here. And we've got our comparator here. This goes into what's called PEX, right? As I said before, producer extends consumer super. What that means is, let me go ahead and give you the full text here. A collection is a producer of elements if you pull stuff out of it. Let me go ahead and there we go. It's a producer of elements if I've got this list and I'm pulling stuff out of it and it's producing these things and I'm putting them in my hands. You need to use extends for that because you need a minimum amount of interface, a minimum amount of information about the things that you're pulling out in order to do something with them. You need to know that they're comparable, or you need to know that you can dump them to double values so that you can use the less than or equal to, right? You need a minimum amount of information. That's when you use a named parameter and you extends. A collection or a thing is a consumer of elements if you put stuff into it, right? And there you use super. That's where we get PEX. Producer extends consumer super. So you just have to ask yourself, what am I doing with the things? Am I pulling them out to do something with them? Or do I not care about it? I've already got it in my hand, and I'm just putting it into this thing over here because it's a consumer. That's what this is doing, right? Producer extends. We're pulling stuff out of the collection. Pulling stuff out of the collection. Is this larger than that? I don't know. What we do is we hand it off to the comparator, which consumes those things. I take those two things and I put it in over here. And it returns something negative, positive, or 0, depending on the relative ordering of it. And this is where I check that out right here. Compare those two things. If it's greater than 0, then our candidate, our maximum, is next. Why didn't they call it the max over here? Right? It's the max value. It's the max function, right? Sometimes it's treated as the min function. Right? I don't think that there is a min function. Why? Because all you have to do is reverse your comparator. Min, there we go. Oh, there is min. What does it do? Oh, wow, okay. They just repeated their code. Guess what the only difference is? I wouldn't have done it like this. What's the only difference? Less than, right? And let's go back to, where's max? Max ends up being, oh, come on. I can't search in here. Oh, well. You get the idea. Max, there's the greater than, right? That's the only difference between these two things. Producer extends consumer super. Now, again, are you going to have to design your stuff like this? No. A lot of work, a lot of thought went into this. Why? Because we're writing this for other people, right? We're writing the library. Other people are going to be using this. Other people are going to be using this for the next 25 years. Let's really think about what we're doing here, right? Because if we make a bad decision now, that 20 years down the line, type erasure, right? We're still going to be living with that. Because of type erasure, right? This is why at some point some language designs just say, screw it, new language version, and not backwards compatible. Python 3, PHP does this all the time. C is notorious for not making changes because they don't want to break anything, right? New C standards come out every, say, 10 years at most, right? And each one of them has very, very small changes, right? C++ is a little bit different. At this point, it's really, really bloated. Unfortunately, Java decided a couple of years ago, we're going to have a new version every 6 months or 18 months or something like that. And that's why we're on Java 19 now, after having been on, say, 6, 7 for nearly 15, 20 years. Right? Anyway, there's my final solution for all of these things. Here's another example, just to walk you through this. One more time with PEX. All right. So here's a very simple version of this. We have a function foo, and it takes in a list of what? Question mark. Right. Everything in Java is an object or a class or belongs to a class. Objects are the most general types of classes. So there's really not much we can do with it. Right. This is an object. We could print it out. Right. We could compute its hash code, but that's pretty much it. Are we going to be able to do anything else with this? No. Right? So we introduce a named parameter, and at least now we can have a variable of that type. Right? We still don't have any information about that type. We can print it out. We can compute the hash code, but nothing else. All right, we'll put in a minimum amount of information onto this bank account, onto this type, so that we can treat it as a bank account, so that we can get its balance, right? And compute the total of all of these bank accounts here. But we really didn't use the type T there at all, did we? So let's go ahead and erase that and put in the question mark there, because I'm not actually using it. Right? No code changes at all here, but it's a little bit more general. However, if we do need to reference that value, we need a variable or something like that. For example, we're taking a list of bank accounts and another bank account, and if that has a positive balance, we'll go ahead and add it to that collection for you. We are now acting as a producer, almost consumer, right? Because we are pulling stuff out to get its balance, or we're not pulling anything out. I guess we are a consumer here. We're adding it to the bank account, right? And we can use both of them, right? We can use T extends bank account, list question mark super T, because this is PEX, right? Producer extends consumer super, right? And if it's greater than 0, we'll go ahead and add it to that bank account. So if you want to read more, I've got some Stack Overflow questions or producer consumer tutorials or whatever. But that's the idea. Basically, you want to make it as generic as possible, so you don't have to write 2 functions, 3 functions, 4 functions, 5 functions. You want one function to do all of that stuff for any type. But you can go too far. 1 function, period, right? There's no information about that at all. So it's kind of like this balancing act. So general, you can't do anything with it. So specific, you have to repeat yourself. There must be somewhere in between. And that's what PEX does for you, right? It says, well, how can I generalize this a little bit more, a little bit more, a little bit more? Too much, bring it back down, and that's just right. That's Goldilocks right there. Right? All right. That is parameterized polymorphism. Any questions on that so far? Again, you can go ahead and put in parameterized types in your design. For the most part, though, you're just going to use them. But understand that when bad things happen, like, that it won't compile anymore because of type erasure, you at least have a little bit of background now that you can go back and say, okay, well, I need to understand that a little bit more, and now I need to read a little bit deeper on it. I'm just here to introduce you to the idea. Right? Just remember PEX. Right? All right, so to wrap up object-oriented programming, because we are going to go on to databases later this week, we're going to cover the solid principles. And actually, I'm going to cover the first one really quick because you're already familiar with it, right? This is just an acronym I don't even know who came up with this. There are at least 2 other acronyms that I know on principles for object-oriented programming design. And we like acronyms. So usually what you do is you come up with the acronym that sounds cool, solid, right? And then you go back and you start filling it in with the actual words. And then sometimes it doesn't work, so you go back and change the acronym or whatever, right? S stands for the single responsibility principle. And that simply means that's a good encapsulation. That a person should not be responsible for address things. An address should not be responsible for person things. So what do? You separate them out into one class for each one of those ideas. One class, one idea. One class, one responsibility. One class, one idea. One responsibility. Right? One thing that we saw, and I think we did address it in class, or at least on your design document if you put enough information in there for us to do so, is data loading from CSV files. Data persistence, saving to XML files. Data saving to JSON files. How many things does that sound to you? 3 things. What should that be telling you? 1, 2, 3 classes at a minimum. Now, our solution, we actually had 4 or 5 classes because we put it into an inheritance hierarchy, and we also used parameterized polymorphism, but we didn't expect that from anybody, right? All we expected was just not a God class where you put every damn one of these things into one class. Right? Single responsibility principle, right? A class or method, I mean, this is also applies to methods, right? Do you want a God method where you put everything into main? Definitely not. And nobody should come out of a computer science 1 course doing some sort of a design like that. At the very least, put one of those things into a function, right? Don't have God classes. Classes that know everything, do everything, see everything. Person class should not be responsible for an address. It should own by composition an address class. All right? There we go. Responsible. Spell correctly. Responsible. Certainly a store class should not be responsible for a person, and a person should not be responsible for a store, right? That much is pretty much obvious. And the reason, again, you want to do this for another reason is the DRY principle. Don't repeat yourself. Right? So most people had an address class. Good. Why did you have that? Because you immediately saw that stores have addresses, people have addresses. Should I repeat myself in those two instances? No. Take that, put it into another class called address. Those two things own that class. But unfortunately, a lot of people didn't realize that you could do the same thing for people, right? This store has a manager. A manager is not a string. A manager is a person, right? It owns something. So that should own a person class. Some people went even further than that and said, well, a manager is a special kind of person. They're very special kind of people usually. But I'm going to go ahead and put that into an inheritance hierarchy, right? Person, manager. And then later on, maybe because I read ahead, maybe there's a different type of person, a customer. I don't know whether or not you're going to need that. We marked down that, great, that's fine to do. Probably, though, Yagni. You ain't going to need it. Right? Don't repeat yourself. The O in solid stands for the open-closed principle. And here's the statement of it. Right? Every unit, that is module, class, method, should be open for extension and closed for modification. And all this is classical inheritance. Right? Let me go ahead and bring this over. Right? Superclasses provide general behavior, generalized behavior, that should not be modified. Right? Once the hierarchy has been designed. Because this hierarchy, once you design this hierarchy, you are done. That is it. And if people are still using your stuff 20 years later, right, that means it probably was well designed, or they have 20 years of frustration. Right? In the subclasses, it was where you provide modification, right? Or sorry, extension. There's some base functionality, but I need to change that. A list holds stuff, but a list holds stuff in an ordered manner. And an array list holds it in an array, and a linked list holds it in a bunch of links, right? That kind of hierarchy where you've got specialization down here, that's what the open-closed principle is. All it means is if you see some common functionality that probably is the same here, same here, same here, bring it up here, right? You can always open it for extension later on. I knew a type of count that is completely different, right? Go ahead and make it. Let's see. Yeah, I'll just bring over the rest of it right now. All right, let's see. I'll bring this over. There. Oops, nope. Sorry, there. All right. So suppose you had well-defined functionality in a superclass and you had 5 subclasses that all depended on it. Suppose that you have a new class that requires different behavior. Do you have to go changing any of those other 5 classes? No, because they already provide their specialization. They are open for, it's open for modification, so we can introduce this new 6th class over here, but it doesn't mean that we have to change anything over here. It is closed for modification. Right? And so the solution might be to modify the superclass, but that's not what you do, right? Because it is closed for modification. If there's no general or default behavior, don't define one. That should be screaming out to you, make an abstract class. Over here, is there a general account that we know how to compute the value of? Nope. So we made it abstract, and we didn't even have to bother answering that question. Right? Again, at the end of the day, you want a well-thought-out inheritance because it's extremely difficult because you are locked into that inheritance hierarchy once it's done. Should an integer class be subclassed to redefine what an integer is? No. That's why Java made it final. It is closed for modification. Right? That's it. That's what an integer is. Case closed. You can never change that. Right? All right. L is for the Liskov substitution principle, and we've actually seen this one too. Modification. Right? And here's the mathematical statement of it. If S is a subtype of T, so we've got T and S, then objects of type T may be replaced with objects of type S without altering the desired properties of T. You've seen this before. It's just simple subtype polymorphism, right? So for example, if I've got Java here, right? If I've got an array list of integers, right? Numbers is equal to a new array list of integers, right? And then I want a different array list, numbers 2, that's a linked list implementation, right? Those are two special types of lists. I could refer to either one of them as a list. I could do this. List of integers, integer, foo is equal to numbers, right? Why does that work? Numbers, there we go. Works due to subtype polymorphism. Right? There's nothing to stop me from making reference to the second numbers. Foo is equal to numbers 2. Numbers 2, there we go. Both of those work. Why? Because an array list and a linked list are both lists. When does it not work? What is a violation of Liskov? Liskov would be the rectangle problem. So do you remember the rectangle problem? If not, we can go ahead and take a look at it again. So we've got, where is it? We've got a shape, a square, and a rectangle. Let me go ahead and highlight all of those into the inheritance hierarchy. And the demonstration that I showed was I created a square 10 by 10. There's my square. Oh, I can't draw a square, right? There's my square. But I had these mutator functions set width. So that it was a 5 by now 10 square. Is that a square anymore? No. You can't take a square and substitute it, or you can't take a rectangle and substitute it, right? It doesn't make any sense, right? So that's a violation of the Liskov substitution principle. That should not happen. So the Liskov substitution principle says this inheritance hierarchy should not even exist. Don't do this, right? Yeah, you could get rid of the problem by taking away the setters, but that really doesn't solve the problem at the end of the day, because and most programming languages have what's called reflection, and you can actually still jump into the class and change it in various ways. That would still be a violation of the Liskov substitution principle, right? Think about all the options that you have in your phase 2 now, right? When you're actually going to be graded on inheritance, you always ask your question of, is A an instance of B? Is this a relationship? If so, okay, fine. If you can come up with one instance where that might not hold, right? Well, a customer is not necessarily a person, right? It could be another company or something like that. Probably don't want to put that into an inheritance hierarchy. A manager is always a person, right? Well, yeah, so maybe that's okay, right? Those are the kind of design things that you need to think about, put on a big blackboard, and then bounce ideas off of your partner. Or at least with rubber duck debugging. Bounce your ideas off of a rubber duck sitting on the top of your computer. And if the rubber duck starts talking back to you, giving you better advice, well, thank the duck and then go to caps, all right? If you're hearing ducks talk, then there might be something wrong, right? All right, so violation of the Liskov substitution principle. The I of the solid principles is interface segregation principle. Now this simply just means that no client code, client code is code that uses other code, should depend on methods that you don't care about. Here's an example. Suppose that I had a click event handler, right? So I designed a graphical user interface, and I've got a button on there, right? And there's a click handler. Somebody clicked that button, right? I need to specify what happens. Suppose that the interface has two methods, though, on click and on double click, right? Because you can click something, but then you can double click something. Do you generally double click buttons? Buttons, though? I don't know. What do you double click anymore? Files to open them up, right? But in a user interface, do you click a button? Not usually, right? So why should I be forced to specify what happens on double click, right? If I'm going to implement this click event handler, right, and there are two methods in there, I have to do both. Well, okay, on click means it's the save button. It'll save the file. On double click, okay, I have to do it, so I guess I'll save the file as well, right? Or I'll go ahead and save the file twice, or I'll have one of those functions call the other function because I don't want to repeat myself, DRY. I got myself into this problem of answering these questions with no good answer by putting too many functions into this one interface. Interfaces should be as small as possible, right? 1, 2, maybe 3, you're pushing it there. Sometimes even 0 methods, right? For example, let me go ahead and pull up my notes again on inheritance with the collections hierarchy. There we go. Take a look at that nice, well-defined inheritance hierarchy for collections. I'll tell you up here with these interfaces, they're at most 1 or 2 or even 0 methods. For example, random access, that has 0 methods. Dec, queue, I think that there are maybe 4 or 5 methods at most, right? And all of them have to be implemented for you to be considered a queue. But you want to keep it as small as possible so that you don't get into this issue of, I have to do everything. Right? Later on, when this will come up later on when you have to write your own list class, right? And you might be tempted to implement the list interface in Java. You just bought yourself a whole lot of work if you do that, right? Because there are going to be maybe a dozen functions that you have to implement. Not all of them you're going to want to implement. Not all of them even make sense to implement for your design. So keep it small, right? Keep it simple. That goes into the KISS principle, right? What's the KISS principle? Keep it simple. We could come up with a better S word that is more positive, right? Keep it simple. Seymour? Okay. Not everyone is named Seymour, and I don't know how to spell Seymour, so something else.
Keep it simple, student.
Oh, student. Oh, okay, the student is fine. Right, yeah, there we go. That's fine. Right? So keep things simple. Keep your interfaces simple. Oops. The last is dependency inversion principle. So for this, I've got a picture. I've just got a picture right beforehand. Here we go. So let me define it first, I guess, before I bring my picture up. High-level modules, that is classes, should not depend on low-level modules. Right? You will see this immediately when we start doing database programming. Right? So there are lots of databases out there. MySQL, MongoDB. There's there's Informix, which is an IBM product. There's MS SQL, SQL Server by Microsoft. There's Postgres, which is free, right? And I can name maybe a couple more. I can name a dozen different databases. What if you wrote code that only worked on MySQL, right? And now you've expanded, right? Now MySQL is no longer enough. We need to upgrade to Microsoft SQL Server, right? Guess what you're going to do with all that code over here? Throw it away, start over, rewrite it, so that you're writing all towards Microsoft's code. Right? That's depending on a low-level module. That's high-level code, my application code, depending on which database you're connecting to and using. We don't want that. We want to invert that. And so this is that picture, where we've got object A and it references or depends on object B. What we're going to do is we're going to separate those out and put an interface between them. That this object over here is going to implement an interface. And then we're going to program not towards a SQL server, not towards a MySQL server, not towards an IBM server. We're going to program towards that interface. And then each one of those different products is responsible for implementing that interface. So that I can take that SQL server, throw it away, bring in Microsoft server, plug it in, and I didn't have to change a single line of code over here. Right? All I had to do was change my configuration. Instead of connecting to that database, connect to that database over there. Right? That's the dependency inversion principle. Here's another example that I was working on right beforehand. Right? Both of them should rely on abstractions. All right? So here's the example that I was working on that is more germane to your project here. Right? So suppose that you have, we're going to be loading up persons from a CSV file, right? So there we go. There's our code. Person CSV data loader foo is equal to new person data CSV data loader, loading it up from a file name, and then we pull out those people. Right? Oh, okay. Now we're going to change it. We're going to change it so that we're not persisting. We're not saving to XML. Right? Now we've got something that saves to XML. I want to now load it up from XML. Guess what I do? Person XML data loader equals new person XML data loader. Somebody, my partner wrote that. Now I need to connect to it and use it. But guess what? To get the persons, one of them has a method called getPersons. The other one was loadPersonData, right? Because everybody has their own way of naming things. Yet again, we've changed. We're going to be loading it up from a database now. Right? So new person database loader, the person database data loader, right? You just tack on more and more adjectives, right? List of people, oh wait, no, now it's connect to the database and query it and then query the person table, right? Because we need to be even more descriptive, right? Add on another one, add on another one, add on another one. Right? Does this seem like a good idea? Nope. So what I'm going to do, I'm going to create a single interface, right? So public, and I'm doing this all just in one file, interface, data loader. I'll say person data loader. Right, there we go. And it defines one method, public, list of person, right? Load data. There we go. There's my interface. And what I'll do is I'll take this person CSV data loader and I'll make it implement that interface. And then this load data, it simply just calls this.getPerson. This one would call this.loadPersonData. This one would call this.connect and query to the person database or whatever, right? And then what does my code look like? My code looks like this. List of person people is equal to foo.loadData. That's all I need. One interface. Everybody else implements that interface, and I only have to worry about that thing in between, right? That one interface, right? All I need to do is look at that interface and say, load the data, load the data, load the data, right? And you can take that even a step further, right? That one is good for what? People? What if I did it even more generally? Public interface. Don't go back and do this, by the way. If you want to as a fun exercise, great. Make your focus the next phase, though. Interface, did I spell it right? Yeah, there we go. Data loader. Now we're not even going to specify that it's people that we're loading. We're just going to specify that it's a list of things, T, right? Because we just talked about parameterized polymorphism, right? Load data. There we go. That means that I need to parameterize this. And now what I'll do is I'll create another sub-interface. Data loader for, and then replace T with person. Data loader, replace T with store. Data loader, replace T with, whatever, what's the third one? Item, or whatever, right? And now I've got one common interface for all my data throughout the entire project. Load data, load data, load data. I don't have to think about it at all anymore because I did the design up front. Again, don't go back and necessarily do this until you've got everything working. Once you've got everything working, check it into GitHub, tag it as working. This is what I'm going to submit if I screw up on this experiment that I'm going to run. Then go back, then do a redesign like this and play around with it, see how it works. And if it works, great, and it still compiles, it still runs in the grader, all right, go ahead and check that into GitHub, right, and then move on, right? But otherwise, if it doesn't work, go back and revert your changes back to something that did work, right? But this is basically kind of something that we did. Right? We had a whole bunch of different classes. Very small classes, very small interfaces, so that we didn't have to worry about all those big giant details in one big giant data converter file. Right? We offloaded them to interfaces, and ideally, I think if you did both XML and JSON, ideally your main should have been 9 lines of code, and that was it. Right? That's what you should shoot for. Right? But again, don't go back and go this far. Yagni, right? You ain't gonna need it. Right? Go far, but go far enough. Because what's better than good? Good enough. All right, on Wednesday, we will start talking about SQL. I'll get you set up and started in the weekly post. We have some things like you might want to install MySQL Workbench. You're gonna want to get your database password.